Hey guys, so this is 2.1, which is limits. So you all have seen limits before. It may have been a while, and I know that it's something that a lot of students struggle with. So it is something that is fairly basic as far as the calculus goes, but it definitely is something that you need to spend some time reviewing if you don't remember how to do limits. So all of the examples that are on here are showing direct substitution. So anytime you have a limit problem, that's how you should start, is substitute the value of x that it's asking you to find the limit at. And if you get an answer, that's your answer. The issue is going to be when you get something like 0 over 0, infinity over infinity, 1 over infinity, something like that. And so we'll look at how you would deal with limits if that's what you get when you do the substitution. But you should always start by first plugging in that x value. So the definition of limit, those of you that took magnet pre-cal, you may have seen a different definition. We are not doing delta epsilon definitions here. So this is a more intuitive definition of what a limit is. So first of all, how you would read this would be the limit of f of x, or limit of f, as x approaches c equals L. So that's how you would read something like that. The notation means the values of f of x approach or equal L as the values of x approach but do not equal c. So the reason they specify do not equal, and then here they say or equal, that it could. So something like this one, this function is a continuous function. So as x approaches 1, the x values exactly equal 1 and the y values exactly equal 2. So if you have a continuous function like that, when you do the direct substitution, you can see from the work down here that you get an answer of 2. The issue would be something like this. So here, as x approaches 1, the function itself does not exist at 1. But for limits, that's okay. So really the point of what they're saying here is you want to look at what are the y values of the function approaching as x gets closer and closer to whatever it's telling you x is approaching right here. And if it exactly equals, then that's great, but it doesn't have to for a limit to exist. So down here, it's showing you all of the work, how you would actually analytically find what the limit is, but we can tell from the picture. So we don't need to go through all of the work if we can see the picture of the graph. But this is how you would show the work if you were going to actually do it analytically or if you didn't have the picture. But you can see for all of these that the y values are getting closer to 2 when the x value is getting closer to 1. This one right here, the function is defined at x equals 1, but it's defined at a different place than it is right here. But the y values of the function are getting closer to 2. So the limit is going to equal 2, it's not going to equal 1. So the limit doesn't necessarily have to equal the value of the function. So here are some properties of limits: sum and difference rule, product rule, constant multiple rule, quotient rule, power rule, and then some other properties. So all of these properties of limits only apply if the individual limits exist. So if they don't, then you can't split it up in the ways that they are showing you here. But all of these should be pretty intuitive. So it's saying something like, if you're adding two functions together and both the limits exist, you're adding the two limits, so you can split it up and do them separate. Same thing with subtracting, multiplying. I can factor constants out. I can divide as long as the denominator is not equal to 0. If you have a function raised to a power, then the limit would be equal to the limit raised to whatever power this is. So basically you can factor that power out if you want. And then some other properties. If you're taking the limit of a constant and there's no variable to plug in, then your answer is that constant. If you're taking the limit of x as x approaches c, then your answer is whatever x is approaching, because if you do the direct substitution, you get c. So polynomial and rational functions, this looks really complicated. All it is a polynomial with the x value of c plugged in. Okay, so a polynomial is continuous everywhere. So if you have a continuous function, then you can do the direct substitution and the limit is going to be equal to the value of the function. That's all that this part is saying here. And a rational function is a function that is a polynomial divided by a polynomial. So as long as the denominator is not equal to 0 when you plug in c, then this one I can do direct substitution as well. If the denominator is equal to 0, then there's more work that we have to do. So evaluating limits, again, substitution wherever you can. If you can't do substitution, then you're going to have to do stuff like factor or multiply top and bottom by something, and we'll do some examples with that. So right here it's saying that trig functions, exponential, logarithmic functions, all of these we can do direct substitution. So be careful with that because you want to be able to have the function exist and have it be continuous if you're going to do direct substitution. So not all trig functions are going to be continuous everywhere. So make sure that when you do the direct substitution that you are getting a nice answer and not something that has 0 in the denominator. If we have a picture, then it's a little bit easier to see what the limit is going to be because I don't have any work to show. I'm just looking at a graph. So as x approaches 0, this one technically does not exist. Usually for something like this though, there's going to be something else they do with it, which we'll talk about in a little bit. But because the function here doesn't exist to the left of 0, technically this limit doesn't exist. We can have one-sided limits, which we'll go over, and if we were going to look at a one-sided limit, then it would, but in this case, it doesn't. As x approaches 1, it's going to be different. The y values are 2 different numbers on both sides, so that's why this limit doesn't exist. As x approaches 2, the y values are getting closer to 1. As x approaches 3, the y values are getting closer to 2. And as x approaches 4, same reason as this one, the function just doesn't exist on one side, so we would say the limit doesn't exist. So one-sided and two-sided limits. Occasionally you do see the little superscript. So the superscript is telling you that you're approaching from one side. So the plus is approaching from the right, the minus is approaching from the left. So the way that I remember it is plus, we are approaching from the positive side, and then the minus, we're approaching from the negative side. So make sure that you are reading the question. If a question is asking you for a one-sided limit, then you're only looking at one side of the graph. In order for a function to, or in order for a limit to exist, so without the plus or the minus, then both the right and the left-handed limits need to be equal. If they're not, then this limit doesn't exist. So you could have both of these exist, but if the one-sided limits are not the same number, then the limit without the one-sided symbol would not exist. So then, just like I was talking about before, if we then specify as x approaches 1 from the right, this one, as x approaches 1 from the left. Okay, so as x approaches 1 from the left, the y values are getting closer to 0. As x approaches, that one should be a positive. As x approaches 1 from the right, the y values are getting closer to 1. As x approaches 0 from the right, the y values are getting closer to 1. And as x approaches 4 from the left, the y values are getting closer to 1. So those one-sided limits do exist. So sandwich theorem, this is also sometimes called squeeze theorem. So you may have seen it before. Different textbooks call it different things. It's the same theorem. Basically, you have 3 functions that create a sandwich or 2 functions that are squeezing another function. So if one function is always greater than another one and one of them is always smaller and you have one in the middle, if the limits of the 2 outside functions are equal, that's going to force the limit of the middle one to also be that number. Now, to be honest, this theorem doesn't come up all that often. It's not something that I would really worry about. I don't know if I've ever seen it in free response questions, but it is how you would probably compute this limit, at least for now. Once everyone knows derivatives and we can go over L'Hopital's rule, there is another way that you can evaluate a limit like this, but for now you would probably want to do it with sandwich theorem. So we know that sine, no matter what the argument is always between -1 and 1. And then here I multiply everything by x squared in order to make it equal to the function that it's asking me for up here. And then the limits of the two outside functions are equal to 0, which is going to force the limit of the middle one to also be 0, because you probably didn't know what that function looked like without seeing the picture. So if you don't have a graph and you don't know what the function looks like, then you need to have some other way of finding the limit. This one, we're not going to go through how you would use sandwich theorem to find this limit. I can show it to you if you want me to. I'm not going to do it in this video, but this is a limit that you need to know. It is something that comes up a lot. It is definitely one that you need to be able to recognize and be able to use. Okay, and the last few examples we have here are going to be some trig limits. So this one, tan x over x, we would want to split the tangent up into sine over cosine. So that's what they did here. And then I can switch the denominators because multiplication is commutative. So that's what's going on right here. And then limit as x approaches 0 of sine x over x, that one is one you need to have memorized. So that's equal to 1. And this one, when I plug in 0, cosine of 0 is 1. So it's going to be 1 times 1. So my answer is 1. So it's using the product rule for limits here. It's just going to be that limit times that limit. For something like this, those of you that know L'Hopital's rule, you could use that. Everyone will know that at some point. But for now, what you would need to do is a little bit more tedious, but you will start to see patterns as you go through some of these examples. So what we want to do is we want to be able to use this limit. So I need this to be a 3 on the bottom. I need the argument to match what's in the denominator. So there's a couple different ways to kind of think about this. The easiest way is if I multiply 3x on the top and bottom. Okay, and I kind of did two things in one, but I switched where the 3x is just so you can see this limit a little bit easier. So I'm just multiplying top and bottom by 1. It just happens to be 3x over 3x. Then this limit right here, as x approaches 0, that one is going to be equal to 1. And then here the x's cancel, and so I'm left with 3/4. And so that would be your answer. This one, I do pretty much the same thing, except I'm going to kind of do it twice, because I want the 3x on the bottom for this part, and I want 4x on the top for that one. So I'm going to multiply 3x on the top and bottom for this one, and 4x on the top and bottom for that one. And again, I kind of did two things in one, so I split it apart, but I really just multiplied by 1. And then here, the 3x over 3x, that limit is going to be equal to 1, so that cancels. Here, 4x over sine of 4x, that limit is going to be equal to 1, so that cancels. And then I'm left with the same thing I had up here. So 3x over 4x, the x's cancel, and I'm left with 3/4 as my answer. So that's the basics of limits. We will do some more examples in class, and in 2.2 we will look at limits as x approach infinity.